Hello and welcome to the Unit 3 review video about antibiotics. This is the start of the antibiotics slides with a bright yellow slide that you've seen. Okay, let's get into it. So there's a lot of interesting history to antibiotics, but that's not what I'm interested in teaching you. I want you to know what they are, how they work, how they don't work, what they are not, so that you can educate people. So kind of start with mode of action. What are the common modes of action? How do antibiotics work? Generally speaking, how would you say that antibiotics work? And what I want you to focus on is that they typically inactivate or interfere with one enzyme in a cell. So you should be able to come up with two examples of one enzyme that is blocked by an antibiotic. And you should be able to come up with several modes of action and example antibiotics for those modes of action. And then the next one is spectrum of activity. So you should know some examples of broad spectrum antibiotics, and I haven't really given you specific narrow spectrum antibiotics, but you'll see when you study the beta-lactams, several of them, their spectra of activity are mentioned. And so this is something to pay attention to when you look at the beta-lactams, because we really focus on that group for a lot of different reasons. And when you focus on that group, you'll see that a lot of times when we develop a new antibiotic, historically, what's been cool about that antibiotic is its new spectrum of activity. They all have the same mode of action. So all beta-lactam antibiotics have the same mode of action. They all block the same enzyme in the same way, but they're different molecules. They interact with cells differently. And so they have different spectra of activity. So make sure you understand what that's about. So in the slides, that would be, where would that be? Mode of action, spectrum of activity. I should also point out, make sure you're looking at the vocabulary lists to make sure you're knowing all the vocabulary. Because I expect you to know resistant, sensitive, some other words, but anyway, mode of action, stuff like that. And then this population model of antibiotic failure, right? The population model of antibiotic failure. So why do I teach you this? This is what lets you understand why antibiotics might start working and help take a patient's signs and symptoms away, and then stop working. And the signs and symptoms come back and get worse despite continued use of that antibiotic. Why would that happen? Well, that's where we would be looking at these mixed populations and what happens to them. And so the two examples of this are why would antibiotics start to work and fail, and then what goes wrong if we stop taking antibiotics too soon. So make sure you're going through this and come back to this after you've looked at disinfection and decimal reduction time and the 3 C's of disinfection, because antibiotics work the same way. They don't kill the cells instantly. They don't kill all the cells. They kill a percentage of the cells in a certain amount of time and the same percentage of the remaining cells in the next amount of time. So between understanding decimal reduction time and this population model of thinking of infections, you get it. You can understand how complex this is, and you can help people understand what might be happening. And the next one, we really go into detail about the beta-lactam antibiotics. Beta-lactam antibiotics. For several reasons. The first one is that these are the most common. So more than half of antibiotics prescribed are cephalosporins, and that's just one group within the beta-lactam antibiotics. So they're incredibly common. And also, I just want you to see this detailed mechanism behind this mode of action. I want you to see exactly what an antibiotic really does in a cell. So when you look in the slides, you'll be seeing this this analogy with making a fabric bigger. Well, explain to me, what does this have to do with a cell trying to grow, and what part of this process is a beta-lactam antibiotic trying to stop? And explain what this is about. Make sure you understand this diagram and what it's trying to show you, and explain it using this terminology like transpeptidase enzyme, amino acid chain, peptidoglycan, carbohydrate chain, transpeptidation, and things like that. And then what would a beta-lactam antibiotic do to stop this process? That's here, where beta-lactam antibiotic is going to fit in the binding pocket of this enzyme. It's going to mimic this thing that the enzyme normally sticks to, and it will fill that up and block it. So this enzyme will never be able to do that reaction again because it's permanently stuck to the antibiotic. The cell doesn't know that. The cell is just going to keep making holes and not filling them. So the mechanism, that's the mechanism of how it works. It's kind of the detailed thing going on, the detailed mode of action. And then 2 ways bacteria can be resistant to specific mechanisms. So what are they? What is carbapenem-resistant Enterobacteriaceae? Why are they resistant to carbapenems and cephalosporins and penicillins? Why is that? What do they have that lets them be resistant? What does MRSA have? Methicillin-resistant Staphylococcus aureus. What does it have that makes it resistant? So make sure you can tell me that. Mechanism. Oops, let's back up. So what are the differences between classes? What are the classes? Tell me the examples. So here you have to know penicillins, and you have to know those are the older ones, like penicillin. And then you have to know about cephalosporins. Why are there so many cephalosporins? What is it about the structure of a cephalosporin that lets us modify it and make so many different versions? Carbapenems. What's so cool about imipenem? Why is it famous? And remember that antibiotics that end in cillin tend to be penicillins. Antibiotics that start with ceph or CF tend to be cephalosporins. And then antibiotics that end in penem tend to be carbapenems. And then the last one is the monobactam. And there's only one, that's aztreonam. What's special about aztreonam? And then the vancomycin detailed detailed mechanism of action. I guess it's just one. How does vancomycin accomplish the same thing a beta-lactam antibiotic accomplishes in a different way? So it's going to block transpeptidation, but it's going to do it in a different way. So how is it going to do that? And how are cells becoming resistant to vancomycin? What does a cell have to do to be resistant to vancomycin? And then last, example, antibiotics and their modes of action. So for this, go back to studying for the mode of action quiz. You're just going to be tested on this again. So this is your slide that tells you what to study. There are quite a few, because there's the ones in this list from 56 to 65, where you can learn as much as you want about tetracycline and doxycycline, but all you need to learn is their names and that they inhibit translation. And you need to know about colistin and polymyxin B, and they disrupt cell membranes. That's all you need to know about them, but you could learn so much more if you wanted to. So that's pretty much it for antibiotics. It is it's a lot, but if you can learn this about the beta-lactams, if you can understand the beta-lactams and vancomycin, how they're related to each other, you'll be able to speak to people in a really informed way, and you're really going to be in a position to help people make better decisions, and that would be awesome. Go forth and do this, and I'll see you at the next video.